All right, let's get started today. I want to introduce our speaker. This is Stephen Fitzgerald. He is from Intuitive Machines. Now, I just want to tell you a little bit. I didn't really know a lot about Intuitive Machines, but one of our former adjuncts, Tim Crane, who worked at NASA and he worked with the UHCL physics department for quite a while. And he worked with Intuitive Machines, and if any of you have known Tim, you got to know that if he's over there, if he left NASA to go there, they're doing some really interesting stuff. And so there was one person, I cannot remember his name off the top of my head, who was here last semester as part of our college seminar series, who gave a talk with that about some of the stuff that they do, and I just found it pretty fascinating. So for the next 3 weeks, we've got 3 different talks. Each is going to be from somebody from that company, and they're all going to be talking about some of the things that they're doing. And you'll notice that as a group, they're actually doing some very different work, but it's all, I think, pretty fascinating stuff. And with that, I want you to also keep in mind that this is a local company. This is one of these situations where if you have questions, they're here to answer them. And if you want to learn more about what they're doing, we have the speakers right here. So with that, I'll turn over to Stephen.
Thank you, David. How many guys? I was asking David about the course, about what the course is, and I love the framework of the course. How many undergraduates are here? Excellent. I expect really, really hard questions from you. Graduate students. Okay, y'all can't ask questions. So my background, I'm going to go ahead and get going on this. I'll tell you a little bit about Intuitive Machines, but I'll tell you about myself first. Actually graduated just across the street way back in 1981. Went to Clear Lake High School. I left here, and then I basically have a bachelor's and master's in aerospace engineering from Texas A&M. And then basically through a co-op program, I worked at the NASA Johnson Space Center. Basically retired after 30 years. And my technical specialty, my technical background really qualifies as physics. It's built on top of physics. It's fluid dynamics, in particular aerothermodynamics, which is reacting flows for reentry vehicles. So basically reacting chemistry, reacting aerothermal chemistry. In addition to that, I moved my career about every 3 years. I adjusted a specialty. Started with arc jets, went to basically generic space shuttle heating, went to space station, which is basically kinetic theory, statistical mechanics, and that really comes into play there. Came back from that, and during that time, had a couple of spaceflight experiments where we were basically, I was the JSC plume expert. The idea is that space shuttle rockets fire in atmosphere, and you get these long straight plumes. If they fire in a vacuum, they go everywhere. And everywhere includes the space station and every aspect of the space station. So we got involved and modified the models for the space station. That's what the 2 spaceflight experiments were for. And then from there, I just went on to other things. I worked Columbia Accident Investigation Team. I was a branch chief and actually moved up to the Constellation program where I was in charge of program technical integration. We had 10 centers putting together this grand plan to go back to the moon. That's the on again, off again, on again, off again, on again plan that we're working towards right now. And then I essentially retired as Senior Technical Advisor for the Aeroscience and Flight Mechanics Division. In addition to that, about that time I joined the Aerospace Engineering Advisory Panel at Texas A&M, my alma mater. And I have a huge interest in the education and the growth of students in college. I contribute to that at A&M, and I have a real, do you have a soapbox here? Really have a soapbox about appropriate utilization of tools. You guys, as undergraduate students and graduate students in the university, you have companies throwing software at you. If you're in an engineering program, you get thrown software for 3D CAD, you get thrown software for analysis, you get thrown software for stress, fluids, and you can just use it. My soapbox, if you will, is Just because you have a hammer doesn't mean everything's a nail, right? One of the things that you know, an engineer, which is not, you know, scientists and engineers, you can tell jokes about it back and forth, but the key thing is understanding the problem. What level of fidelity, what level of rigor is required to give you a useful answer to the problem you're being asked. So you don't always have to go to the nth degree. I'm going to show a lot of nth degree stuff, but I'm also going to show more basic fundamental engineering that goes into answering the questions, because that's ultimately my job. My job and the job of Intuitive Machines is to basically engage with our customers, outline, pass it up, and basically solve the most difficult challenges with the framework, the vision, the approach that we learned at NASA. So we've got about 40 engineers. The idea was we would come out of the back gate of NASA, take our years of experience and lessons learned and our rigor and discipline that we developed and learned at NASA and apply it to aerospace, medicine, and oil and gas in the Houston area. I joined, I think right now I'm about the employee number 5 or so in the company. I've been there a good long while. I brought my customer, one of my customers with me, and we've been doing work and really chasing some interesting problems. I pretty much made my career solving problems that other people think are impossible or intractable, and I love doing that, one, because no one has real high expectations. It's an impossible problem, but 2, you have to be creative. And so that's what this is all about. The level of work that we're doing in the oil and gas industry is groundbreaking. On the NASA side, I grew up with the development of CFD. Computational fluid dynamics is the solution of the governing equations of fluid. In viscid, they're the Euler equations. Viscous equations, they're Navier-Stokes. My aspect, you know, the job I was trained on, aerothermodynamics, you have the Navier-Stokes equations and then 11 coupled thermochemical equations. They're very stiff, very difficult to solve. Those are the equations that we solve on supercomputers, and we've gotten really good at it. The statement I made earlier about you guys getting thrown tools is that you can go right now out to the internet, you can identify, do a search for CFD codes, and then type open source. And you will be able to download and run CFD cases all day long. If you have access to a commercial tools are designed to give you an answer, even if you give it garbage. The challenge of doing this type of work is knowing, is it right? How do you know your solution is correct when no one's ever solved that problem before? And that's one of the challenges that we face. What we do, these cases that you're seeing, you're going to hear a lot about, some of these. I'm not going to talk about all of them. But the idea is these are full-scale, real-world problems being attacked with high-fidelity engineering tools, being applied by people who have dedicated themselves to understanding the tool, understanding the assumptions that go into the tool, how to use the tool, how to validate the tool to get a correct answer within our scope, within our ability. So everything we do is full scale. On the NASA side, we had ground test facilities, wind tunnels, numerical simulations, but we didn't call it done until we got the flight data. Which gets me to my favorite quote of all time. So we're talking about modeling. We're talking about challenging problems. And George Box, this English statistician, who actually was on the faculty at University of Wisconsin when I went up there and engaged with those guys. All models are wrong, but some are useful. This is so important for physics students to understand. This is important for engineers to understand. This is important for parents to understand. We think we're right all the time, but sometimes we're not. From an engineering standpoint, I can sit down and try to solve a problem with the Navier-Stokes equations as deeply as possible and think if I'm using a high-fidelity tool, I will get the right answer. However, the Navier-Stokes equations are an approximation. Turbulence, closure, turbulence models are an approximation. The Navier-Stokes equations break down as you get more and more into rarefied flow. They no longer apply because the assumptions they're built upon which is this constitutive stress-strain relationship, break down. So what's key is that when you go into doing an analysis, when you get handed a challenging problem, you first have to understand the problem and then pick your tool. You have to understand what assumptions you can safely make about solving your problem, which variables are well known, which ones are unknown, and choose wisely. And so there, that's my soapbox I've gone through. But I also love Einstein's quote, and I believe he basically quoted this when he was being asked about theory of relativity: as simple as possible, but no simpler. In other words, have a model that you know is wrong. It's good enough when you simplify it down to the critical fundamental thing that has to be simple, that has to be modeled, and no simpler. You can go too far on both sides. What you want is the sweet spot in the middle. So I keep these in mind, and trust me, our young guys hear it from me all the time. Just because you have a CT code doesn't mean it's a good solution, and just because you have a tool doesn't mean it's the right one. So this particular problem we're talking about is hydrocarbon releases. Back in 2010, we were all very familiar with it because it was on the news every day. BP blowout, also it was the Macondo wells, 5,000 feet of water. Basically, they had a kick, they were losing mud flow, and essentially they lost the platform, lives were lost, and at last count, I think it was $57 billion that it cost them. Oil flowed for about 70 days, the last number I calculated. It cost BP $30 million for every hour that the oil was flowing in the Gulf of Mexico. What I want to do is say, with some prior analysis, with some engineering analysis on the front end, if I save you 1 week, if I save you a day, that's $750 million. Right? If I save you a week, give me $1 billion, let's call it even. It's about understanding the value of the work that we do. And in order to get that kind of funds, they haven't yet, by the way, they've not yet given me my $1 billion, or I wouldn't be here giving the talk. But it's not just the big BPs. It's not just the big massive blowouts you see every day. One of my customers that I will talk about has had an ongoing response in the Gulf of Mexico for decades. There are just sheens every day, and he's still getting hammered by environmentalists. He's still getting hammered by the government. The Coast Guard's National Resource Center receives over 20,000 calls a day, which are reports of environmental releases. It could be a guy at a gas station who basically just kept pouring gas, was talking on his cell phone, kept the pump going, and was unaware that the gas was spilling out. That's a release. Or it could be a pipeline in the Gulf of Mexico had a failure of a valve. That valve is leaking, and the customer knows it. They haven't been able to shut it down, or maybe they have shut it down, but yet there's just oil out there. If you take a boat and drive through the Gulf of Mexico and you see a sheen on the surface and you report it, it gets recorded. The challenge is, how do you attribute these releases? Who's responsible? And that's one of the things that I'll get to when I talk about my customer. This is an example, and I'm going to do this. I'm going to make sure this is muted. Hydrocarbons can be oil, gas, and basically mixtures of slurries in between, typically multi-phase. At the reservoir, everything's in the liquid form, but as it comes up to the atmosphere, it comes up to the surface, pressures drop, gases come out of solution. And in this case, this is actually in the Bay of Bengal in India. And this, I thought the Earth was deflating when they told me this number. This is basically about 600 million cubic feet of gas per day, flowing from a depth of 800 feet and getting to the surface. Tough to judge scale in that, but edge to edge, that's about 600 yards. The hydrodynamic jump in the middle was this high. There was enough momentum in the fluid coming up that actually raised the sea surface level. Now, I've got many tools for doing this. I've got a great engineering tool developed at Texas A&M. It's the Texas A&M Oil Spill Calculator. It is open source. You can go download it from GitHub if you want. If you're really interested, then come talk to me about a job. But I apply that model, and so here's basically the simulated release. Gas velocities, color by velocity, gets to the top of the surface, and it's doing about 2 meters per second. If you do rho GH, you'll get the appropriate hydraulic jump for that. But it looks nothing like what we see on the left. This diameter of the sphere is the diameter of the main core plume when it arrives at the surface. That sphere actually matched within 2 meters what they observed in the field, and that's right in here. Playing that again, this little area right here surfacing, that's 80 meters. That's why this is so large across. The question is, what are those other rings? What else is happening? What's going on? Because they're not part of a simple model. So the model I chose to model this problem with was too simple. So I wanted to understand it. So I went to another methodology and got this solution here on the left. And all this is me trying to understand what those rings are. What do they represent? What's going on? So I modeled a buoyant fluid coming to the surface, and then also modeled a sea state, and the two interacting. And from watching this, what happens is this fluid, which has a mixture of gas, methane, and water, because when this thing's coming out, it's in training, and so you get this mixture of gas and water that comes to the surface. It has momentum, and when it breaks the surface, most of the gas is released. So now the fluid that falls back is less buoyant than the fluid that was coming up. So it dives under, gets into basically just standard salt water, seawater, and is now more buoyant, and it comes up and releases more gas again. And what you get is this ring of concentric, basically dives and dips and rises, and each time you release a little bit more gas. The net shape of it is influenced by the sea state. There's a net average velocity, so you get a blunting at the surface and a trailing out at the edge, which, when I take this and adjust for it, is what we see in the field. So what I've done is I've used two tools, neither of which are highest fidelity, to understand the problem. Because the application is, where can I safely position ships on the surface to do an intercession with that well? They needed to know where they could safely position people, how far away is safe. And so this is that key to understanding the problem. This is not numerically correct, but it represents enough of the physics to allow me to understand the fundamentals of what's happening in the real world, and now I can take and engineer it. And so the interesting thing is, if you're drilling a well in the Gulf of Mexico, you have to have a plan in case something happens, in case a BP type blowout happens. Now, the majority of customers in the Gulf of Mexico assume they can do a BP type intervention, which is the oil's flowing, I can position a drill ship, big massive ship directly overhead, and I can lower my intervention apparatus on a drill pipe straight down. Maybe, maybe not. It depends on ocean conditions, currents. And so one of the things that our tool did is we went into predictions for the oceanographic environment. In this case, it's HICOM. It's the Navy's high-fidelity Gulf of Mexico model. They've got it around the world. And I can extract predictions, and I can simulate, in this case, 6 years of a release from one location. And every dot you see is a simulation. That's the same release. The difference whether it goes left, right, north, south is all a function of the current and the salinity and the temperatures in the environment. So if I'm a customer and I'm trying to tap that well and I look at this picture on the right over here, very seldom, very small percentage of time will I be able to be directly over the well because that's where the plume is. Again, informing our customers decisions that matter to them without having to go to great lengths to do it and pull together the highest fidelity tools. This tool is useful for making decisions. If I have a customer who, like this one, if you thought you're 3.5 million per day, this is a simulation of 3.25 billion cubic feet per day released. Difference is it's at 5,000 foot depth. Notice this is a very high, this is compressed methane at those depths. It has a density much, much lower than oil, but it's still liquid. And when it comes out, it screams. And because it's coming out so quickly, it's turbulent. It's chaotic. It generates terabytes of data for 1 second simulation, because in order to capture the appropriate scales in the fluid dynamics, we have to have a very high resolution grid. The higher the resolution grid, the smaller the time step you can take, and it takes a long time to run. But if we need to do some engineering analysis with this, how much force, if I put a stack in this, if I put a piece of hardware in this flow, how much force is generated on average? Well, this is not the one that's going to directly give the answer. I could do it that way. I could put a piece of hardware in there and run a CFD case, and you'll see one that looks like that later. But if you're trying to design an operation, if you're trying to make decisions about how to do it, you need to make decisions quickly. If you're out there in the field and you need to know, is tomorrow better than today? Is this piece of hardware or that piece of hardware the right one I want to apply today? You need to make quicker decisions. So we do that, and we develop case-specific engineering models. When I say engineering model, it sounds like it's less than a complete physics model, which it is. All models are wrong, but some are useful. Engineering models, we develop a model to the level of fidelity that's useful to us to apply to the problem. And in this case, we're always focused about coming in where the force is the highest, down close to the blowout. And so we do high fidelity fits to the flow field. And now this is 2-3 equations that I can put into a program and do simulations very rapidly, very easily. That's great for the high velocity gas, but I had to adjust my model because one of my customers had this flow field. Whereas the other one was 40 meters per second, this is 1.5. It's an oil, and so it's moving slower. The challenge with this is when you look at this simulation, you'll see those blue streamers. That's actually water going backwards and down. That water is being drawn in and down into the flow, so that it's actually mixing with the flow in the pipe before it comes out. That invalidates my approach for the model you see on the left. So, chance for you to get creative. And so what we did here in this case was we looked at the exit plane of the blowout, and in the picture on the right you see clear areas. Those clear areas are where water is going down. And so it pushes the oil off to one side, and it is dynamic as all get out. Let's go play this. So this is a 10-second simulation we did. The color of that dot that's moving around is the average velocity. The placement of the dot is the velocity centroid mean, basically where I can say that's where the blowout, where the forces are coming from. And so now I've got an unsteady solution that I can track those things, but I can also take it into Fourier space, identify what dominant frequencies are of the flow, evaluate that against, again, from an engineering sense, what's the natural frequencies of the system I'm lowering over it, and calculate whether or not I need to be concerned about it. In this case, I did, but these are different levels of engineering models that we apply. Again, appropriate to the question at hand in the time frame that you need the answer. All of these are valid models. All of these are valid applications. Oh, sorry, there we go. So back to the fluid structure interaction piece. Depending on the velocity and depending on the question being asked, I can use an engineering model or I need to go high fidelity. The one on your left, my right, is that gas case that you saw surfacing. And this is a flow field going over and around and through a capping apparatus. In this case, they built it from land-based stacks, but most of the hardware they build has these little tiny, nicely laid out, machinists love these nicely laid out lines of hydrodynamic lines, about 1/4 inch in diameter. Might have 10, 12 of them in a row. They all come out and they bend and they flow together. It looks nice. But you've got a thin, critical piece of hardware, hydrodynamic lines or hydraulic lines that you count on that are cantilevered in a flow field that's high frequency, oscillations at 100 psi, change in pressure. The challenge is you will fatigue your hydraulic lines and they'll break. This is critical information to decide how do I design a piece of hardware to go into this. Without this information, they go with the standard one, and it doesn't work once they get it down there because all this aerodynamic flutter has fatigued the lines and they've broken. The one on the right, again, is that the very, very slow case, and that's supposed to be playing. It's not. In this case, it's moving around, and this was where it was coupled to. And basically, the fluid frequency surrounded the lowering system, the deployment system frequency, so we have to look for interactions. Luckily, the forces were low enough, and hydrodynamic damping was there to dampen the motion so it didn't actually excite anything. But again, you have to look and understand the problem within the scope of basic first-order physics. The natural frequency of a spring mass damper system is useful. It's one equation, right? And you can analyze it and get the basic frequency that's first-order accurate to evaluate whether or not you need to look for second-order impacts or not. Right? It's all about what level of fidelity is required to solve the problem. Now let's talk about my customer, the guy that had basically a release in the Gulf of Mexico. It's an active sea response. He's continually, being asked about it. The Coast Guard's still saying, what are you going to do about it? It is daily overflights. Every day they fly over this thing. And every day they do, it's in a different place. And it looks different. And they calculate different volumes. Today, they observe 3 barrels of oil effectively on the surface. 2 days from now, they might observe 100 barrels of oil on the surface. And the next day, it might be in a completely different place, another mile down, a mile away, and barely be visible. The challenge of this is they're only getting a piece of the picture. So what we were all brought on board to do was utilize our expertise, our simulations, and evaluate all these observations. In this case, they actually went out into the field, deployed sensors to measure the environment. They took samples on the surface. They had a total of 51 observations, and we were to say, look at all those observations and try to make sense of them. So you're going to see something that looks like this. Basically, here's the simulated release location, and then all of these dots. Those dots represent different methodologies, different assumptions, using that Texas A&M oil spill model I used earlier, plus another one that we developed. And in general, you'll also see an observation. So in this case, the observation is the green circle. It's at the center. You have an uncertainty with the ability of the pilot to locate it. And so in this case, we did pretty well. And these are all for different size droplets, so basically 6 to 4 millimeter droplets dead in the center of this thing, and that's great. But when we come here now, this is another example, different day. We've got different sets of data. ADCP is acoustic Doppler current profiler. That's velocities in the flow in 2 dimensions from seafloor to the surface. CDT is essentially salinity, temperature, density type information. Turned out that the CDT, that extra information, really didn't change our answer, so we didn't need to use that for the simulation. Currents definitely do. So this is kind of nominal for us. We really did a good job with this model when we used the measured data. NGOFS is the Northern Gulf of Mexico Operational Forecast System. It is the highest resolution that they have. It's a high fidelity simulation of the flow. They've got one for Clear Lake, Galveston Bay. It has the highest grid density. It is considered the most accurate. It got less than, I'd say probably about 45% match with the observations, whereas my tool got 96% with the new data. But that's typical. But here's the question. When you look at this, one of the things that understanding the problem is sometimes not just the physics aspect of it. My customer's problem was not that he had the release. My customer's problem was not that he did everything he could to solve it. It was not that oil was showing up on the surface. It was that people were reacting to the oil showing up on the surface because it's an emotional topic. People should care about the environment. We should be concerned about whether or not releases in the environment are going to harm life, harm vegetation, impact our basically standard of living. So those are emotional answers. People react to what they see. So looking at this, in this case, you might assume that the oil slick is kind of going in that direction. I did initially. But using the measured data and simulating it, it actually does this. So it comes up and initially goes down south and then takes a right turn. That was something they'd never observed before. And so sometimes it's here, but all of it flows. What's happening? And why is it important? So in order to address that, we actually did a volumetric release. What you saw was actually just the surface particles from that volumetric release, where we said, all right, particles have different sizes. Oil droplets do. Oil droplets have different sizes that come to the surface at different velocities. Therefore, they get carried further away or closer to the source. Currents move them everywhere, so let's bring in the full current data. And ultimately, in this case, we wound up simulating 250,000 trajectories at a hundredth of a second and less time step over hours. And it opened a lot of eyes. So I'm going to show this animation. This is the animation of the release at the bottom. Notice how dynamic it is. The blue are the smaller particles, the red are the larger ones. That was fast. Let me play it one more time. This we did not expect. The currents at that location in the Gulf of Mexico are so dynamic, they change minute to minute. They'll change 180 degrees, or in the case you saw, 90 degrees in a matter of minutes. They'll change at the bottom different than they change at the top. You can have flow go in different directions, bottom and top. And it was like eye-opening for people. But again, is it good enough? Here's what we saw. Here's the observation. And it's kind of hard to see. I tried to get as much contrast as I could on the visual, but I'll show it to you. Essentially, here's the release point, or the pilot observed source, and then you see these typical oscillations. They look kind of like a laminar flow meandering. And if I were to count those, I've got 1, 2, 3, 4. I got my simulation. I get 1, 2, 3, 4. And then up here, it's hard to see, but it takes a right-hand turn. It takes a right-hand turn. So this is 20 minutes after the pilot did the observation. So we match the location, and now I match the shape and the direction it's going. Here's another example. Pilot observation, simulated prediction. And this is a very, very simple model. I had 3 and 4 knobs. I was ready to turn to get a better answer, but I don't need a better answer. Because what I can do is I can explain what you see. And that was the emotional answer that people needed. There was sonar, there was active sonar that was going on out there. They were taking samples. 4 different lines of attribution all reached the same conclusion. But the nail on the head was the one they'd never seen before. They'd never seen anyone match it. More examples. This is the picture that was in the announcement. Essentially, here's the predicted sheen, or the observation, and here's the sheen. In this case, I was able to adjust the droplet size to get it to match the pattern. So now I've got an idea of what size droplets are actually coming up. This one, same thing, but much shorter, a different dynamic. And all of these are exactly the same volumes from exactly the same place, just different times. All at the same depth as well. That is about 460 meters, call it 1,800 feet, a little bit more, maybe 2,000. It's got a lot of water to come up through. The interesting one I love is this one. These are a phenomenon in the Gulf of Mexico that if you're overflying the Gulf, you'll see those. They're called laminar cells. It's an interaction between a very low velocity crosswind that's perpendicular to current. And so it sets up these little counter-rotating vortices at the surface. And I didn't model that in my data. I didn't model that in my methodology, but the data we plugged into it was good enough to actually start seeing some of that. These last 2 are a couple of my favorites. Lots of times people will see multiple droplet sizes coming together. They never understood it. This is one simulation. This looks like a piece of taffy that's twisted. So basically this thing is moving back and forth like this, and it's overlaying itself. And then you can see the same spiral patterns in the observation. In this case, it was high wind, so you didn't see it get as much clarity. This case is another one where if you look at the observation, you've got an edge here, then it shifts, and then the edge goes on. And I plugged in the pilot observation time, I got this. But when I plugged in and did a simulation, 20 minutes, actually an hour passed when the pilot said he took the data, I get this. And so in this case, the pilot observation time was wrong. He marked it down wrong. So I was able to match when I got the right data in. So Scorecard, essentially, we were the first to actually try to match everything the pilots observed. Everyone else just cared about location. So we evaluated against location, shape, direction, size, and compared all of those things. And in aggregate, with a very, very simplified model, we were able to match 96% of the observations, which I was very satisfied with. Simple model. Simple as possible, no simpler. Now, I said this thing's been out there for decades. We only took data from February 27th until March 15th. They've got years of observations. So what can we do? Can we learn from this? How can we take what we've learned here and apply it? Well, it depends on a couple of things. It depends on understanding the currents at the site and understanding what variables you can actually compare against. And in this case, here's the observed sheen, and it has a cyclic pattern where it gets longer in the summers. If you understand the Gulf of Mexico, if you take the wind speeds in the Gulf of Mexico, they get lesser in the summers. Winters are always more dynamic. If you look at the annual flow of the Gulf of Mexico, it has a cyclic behavior, so we can expect that there would be a cyclic connection between all those variables. And the interesting thing is, if we took just the horizontal velocity at the surface, let's pick a direction north, turns out the Mississippi River empties out very close to this site. And if we take within our measured window the Mississippi River outflow volume, and we plug it into what is basically nothing more than a momentum equation, where you say I've got a northern velocity at my site that's reacting to creating a head pressure for the Mississippi River flow, and the Mississippi River flow, a two-dimensional release will spread at a certain angle, and within a factor of 50%, theoretically it should be about 10,000, that scale factor, if you will. If I apply a scale factor of 15,000, I get all these peaks lining up on the predominant shape. All these variations in between are fluid dynamic interactions that happen. It creates vortices when two fluids mix. You've seen it pouring creamer into coffee. And those vortical structures are what give it the dynamics, but in general, it scales. So that says I can take my Gulf of Mexico or my Mississippi River flow, make an estimate about where these velocities, what directions they're heading at the surface, and do predictions. And so 5 years of predictions gave me this. This is what the maximum possible spread during the observational period was. And the color of those dots is by time of year. It's not unreasonable to expect that you have predominantly seasonal currents that are at play. So within the simple model, we were able to track all those releases over all those years to a single point. And we actually got to within 6 meters of the location on the seafloor that they thought the release was coming from with simple physics. And that's the end of that presentation. Let me just give you a quick, oh, thank you, go ahead. So all of my customers have unique, challenging problems. They're not all good stories yet. This one particular customer, the government's holding about $750 million of his money and the conclusion reached from the team is any intervention is just going to make it worse. And so he's trying to figure out, work with the government. So how can you give me X amount of money? In that particular case, every bit of money that's returned is going to go to the inner city of New Orleans to fund inner city programs, because that's what the company has dedicated itself to. Other customers, more business related. I've got one customer who's trying to drill up in the Gulf of Mexico. We put together a model for him. The government spent $1.2 million trying to prove it wrong. We had a peer review. At the end of the peer review, everyone said it's appropriate, it's good, it gives a good answer. We're still trying to get, in his case, he's still trying to get the government to give him approval to drill. So in all of those cases, though, I know that I've done everything I needed to do. I've given my customer the best answer I possibly can. I've given him understanding for his problem he didn't have initially. It helps arm him in his discussions with the interested parties. And all we did was apply physics. That's it. That's what I got. Now, questions? Undergraduates, come on. Yes?
Someone getting into going into programming and wanting to sort of go down that road of modeling, what is the life after that? What is the things? Like, what would you suggest that you would begin to start passing as far as like 3D CAD, C, Hydrocarbon Releases?
Yeah.
Where would you go?
I'd like to say it's the dinosaur program that I started in, Fortran, but probably not. Actually, we've seen, by the way, all this work is either done with tools we've created or open source tools. I love the open source environment. And the reason I love open source environment is not because someone else has done the work, but because they give you the source code so you can read it and understand how they did the work, and therefore derive the assumptions that went into it. C++ is the strongest, fastest piece that we've got. A lot of my tools I've been working with GPU computing for years. I've got 2 Titan XPs in my workstation at work. Any video game you pass by that passes down the hallway pees itself when it sees that machine. But I can get 10, 11 teraflops of data if I program correctly on the GPUs. GPUs are great for particle-based solutions. Classical CFD is still supercomputer-based. Those are actually now getting more to heterogeneous programming, which is basically using the GPU for what the GPU is good for, and the CPU processing basically large grain, small grain parallelism. And that is, most of that is still C-based, but I call it a cancer. Python is up in everywhere, right? Python is a cancer if you're reading someone else's code. It's the savior if you're writing code. It's very easy, and I like the fact that it's an interpretive language. You know, just run case, tweak a parameter, run case, tweak a parameter. And a lot of the open source world, particularly in the data analysis side of things, if you pick up a version of Anaconda, the Anaconda environment, data processing is just massive. On the machine learning side, Python's coming up, but it can't keep pace with NVIDIA and the GPU speeds. GPUs are killing it right now for machine learning. NVIDIA is owning the world on machine learning right now. But C++, C, any structured object-oriented programming. Just please, when you write programs, don't make them so overly object-oriented that people can't figure out what's going on putting the pieces together. I still do blocks of code. One guy hates me because he says if it's more than 20 lines, you've put too much in it. But that's what I do. Good question, by the way. Any others? Yes? Bessie? Yeah, it's Bureau of Safety and Environmental Enforcement. Steve Ausmus talks about this? Well, you got a better understanding of it from me. He's my boss. Who's it? Beth has moved on. Yep, she's moved on to different companies bidding on a facilities contract for JSC. We've had people come and go. Beth was part of the originals. I was closely followed, followed behind her. But yeah, Steve Ausmus likes the work that we do. So I can give you the background. He gets the sales pitch. What's that? Yeah, oh yeah. If you're into Bitcoin, if you want to crypto mine, you can buy pre-configured machines that have 8 GPUs. I've got an 8 GPU plus 96 core computing box at our site that we use. So it gets it done. But we generate terabytes of data. I'm trying to talk them into buying solid state drives because transferring data is killing us. Anything else?
Speaking of, you talk about generating terabytes of data like constantly. What do you do for your data storage management? Because like I know, like at CERN, they have the gas and okay, you're going to keep this looks good, and then a lot of it have to throw away because it doesn't seem to be useful. So I'm assuming you run into similar problems.
Oh yeah. We've got the challenge in that the customer has paid for us to generate the data, so we have to store the data, and we store and manage the data. So each customer gets about a 6 terabyte drive, and that's enough for about 4 solutions. But what's interesting in the way they're going is if you know what you're looking for, it's basically concurrent processing. So if I'm looking for the force on a piece of hardware in a very complicated solution, if I don't want to try to move my terabytes of data back and forth, I co-process. While I'm doing the computation, I take a flow field and I process it for the information I want, and I save that information. But you have to really know what you're after. For example, VTK, Kitware, by the way, if you guys aren't familiar with Kitware, it is a company dedicated to open source, and they have a product called VTK, which is a graphics programming foundation in C++, and they've basically runs on a GPU. So while you're doing your computations, if you've got a GPU-based solver, it doesn't have to transfer data. It just changes the owner of the data. It goes from the compute node, they change the owner to the VTK-based, the processing node, they generate the data, they change the owner back, and now the compute goes on forward. So a lot of people are really doing the petascale, exascale type computing is challenging, and one of the bigger problems is data. So the key is to understand what you're really wanting from the solution and get that while it's running. We like using the facility we've used the facility up at University of Texas before, the TCAS facility. It is, but even Amazon Cloud you can use, but getting the data, that's where they charge you.
Yeah.
So if you know what you're looking for, you've built it into your processing. Yes?
As far as doing modeling, y'all also focus on if the gas gets out into the atmosphere, what happens then, or not necessarily?
Well, no, we do. For one of my other customers, I did a blowout simulation, and the question was, if you light an oil well on fire, how much oil escapes unburned? Well, someone else wanted to know, okay, well, if it escapes unburned, where does it go? Right? Positioning ships on the surface relative to a blowout. It's a function of the direction the wind is going, and then mixing. Most of the models I've used at this point are basically Gaussian plume models, assumed diffusion, just classical diffusion of a cloud. Basically, the national, they're working with EPA. They've created some tools for doing large eddy simulations of that, so you can have terrain and they can solve it, and it's full Navier-Stokes. Again, it depends on the application. Everything we're doing right at this point are more simplified models, because typically I'm going to run hundreds of cases. My simplified plume case, I ran 150,000 simulations in a matter of 3 minutes. The volumetric one takes 20 minutes to run, but it takes 20 minutes to run because I wrote it in Python because I didn't want to deal with it. If I'm still going to put it on a GPU and it'll execute in seconds. But my boss says, let someone else pay for that. Lesson in business right there. Anything else? Another question? Yes?
What type of sensors are you using to collect data to come up with this model?
I'm sorry, say it again?
What type of sensors are you using? Are you measuring temperature, speed of the water? What sensors are you using to come up with this model?
Let me show you real quickly. I'm just going to pull up, and this should be on slide 3. Yeah, nope, 4. Sometimes you have to build your own sensor. This picture on the right, I went up to Wyoming and there was a drilling pad on fire. It was, to me, I got a bad reputation because I literally stared at it and said, "It's the most beautiful thing I've ever seen." The guys trying to kill it didn't appreciate that. It actually, if Metallica had a pipe organ on stage, this is what it would look like, okay? But no one had ever thought to measure a blowout. There is so much unknown about multi-phase, in this case, supersonic flow. When it comes out of atmospheric conditions, when you look at a picture of a blowout, it has a shape that looks like a rocket nozzle at the boundaries because it's supersonic. And no one understood what's the momentum of a real blowout, how quickly does it change? So we built a sensor pack to take temperature and pressure, and it was surprisingly descriptive. This picture on the top is temperature, and when you go from here to here, you're going from condensate, which is a liquid, it evaporates. As it evaporates, any remaining fluid is what? Cooled. And so just looking at the temperature and pressure combination, we can discriminate gas, condensate, water. This picture down here is an acoustic spectrum. And where you have 100% water, you've got a loss of all your high frequencies. Water is known to damp acoustic frequencies. So in this case, we built it. That acoustic piece, that's an iPhone. I literally just recorded the spectrum. For the sensors in the field, acoustic Doppler profilers are big, massive things, sonars, and the data processing is pretty significant. But it can be as simple as pressure transducer, thermocouple. That's what that one is. Whatever gets you useful information. How's that for a escape all answer? It's like saying, it depends, right? But whatever you need to get the data. I mean, I've gone as complicated as electron beam time of flight velocity measurements that were difficult to take, easy to interpret. Typically, the measurements that are easy to take in a complicated phenomenon are very difficult to interpret. So we got to play that balance. That's why universities exist, to come up with very, very complicated measurement systems that get at the root of what you're trying to measure, but you can't always get to that lowest root, the piece you really care about. And that's where having the understanding of the physics says, if I measure temperature here and pressure, and I know it's a gas-fluid equilibrium system, if I can model that, I can make basically make a calculation of what phase fraction is, for example. So if the first order physics is correct, I can make simple measurements and interpret them. But if you don't understand the low-level physics, you've got to go to that higher, more complicated measurement system. And that's drawing on my NASA experience more than anything else. Yes?
That example you had from off the Indian coast,
yes.
It seemed so regular, like well, it reminds me of convection flows and gravity numbers, or below the Clayton numbers. But there's no, I guess in these cases you don't have a temperature gradient where you have increasing temperature going down, but you do have buoyancy to convection that model to help you much?
It's very similar, right? So in one case, gravity, the buoyancy effect is delta T. Change in temperature gives you change in density. Change in density with gravity gives you buoyancy. In this case, we just start straight with change in this. It's 1,001 difference in density between the gas and air. But as it goes up, the effective density of the fluid gets mixed and more approaches the density of water. If it stayed just gas, one bubble coming up, it'd be, you'd have a hole in the ocean by the time it gets to the surface. So Weber number, the viscous forces that are fighting to pull the bubble apart is balanced with surface tension trying to keep it together. And so there's a maximum size bubble that's stable and can stay there. Everything else breaks up as it goes up. So you wind up with millions and millions and millions, or billions and billions, I don't know, Carl Sagan thing, of little tiny bubbles that get to the surface. And that, oh yeah, very, very similar. It's what if you have a heat hitting a surface, or hitting a roof, it hits the roof is cooler, it cools the fluid, heat transfer, and then it comes down and gets back in the train. Same thing. Very similar. Good application to fundamental physics. Similar systems. Yes?
On the model where you showed the clear area that indicated water, is that actually water back streaming into the pipe?
Yes.
Wow.
Oh, I replaced it. The page up. Yep, the page before this. Page up, page up. This video is the actual mixing that takes place in the pipe. So these are the blue streamers coming in, and this is the fluid coming out. And look at the complexity of the mixing in this. We do this. Get out of it. I'm modifying my charts real time so you can see them better.
Those streamers are actually flowing in.
Yep, flowing in. And the reason is, as the gas comes out, it only expands at a certain rate. It's a classical turbulent jet. Classical turbulent jet has a 22.8 degree angle of spread. That's, if it's turbulent and it's a jet, that's what it does. And that cone doesn't fill the full volume, and it also doesn't have enough pressure to push all the water out. So water streams in. The case in India had a similar problem, but it was a higher pressure. And that one, the water would stream in, build up back pressure, and then the plume would blow it out. So that was like percolation. If you're, you guys probably don't know it. Everyone drinks drip coffee or cappuccino now, but back in the day, I woke up to my sounds of my parents brewing coffee. That sound, percolation. And it was a similar phenomenon. And what that one did, it generated frequencies that were so far apart from the classical turbulent frequencies for that flow that it was just another frequency we had to look at. And that, a little bit more chaotic. Yeah, but this is, I love this kind of stuff. But mostly I do CFD, different than typical application. I do CFD to develop engineering insight. And I stare at these things and figure out what's going on, and then I figure out simplified ways to model it. Get the same character of the flow, but without having to use CFD code to do it. That's the fun part for me. Yes? Yes.
Are those angles, are they formed like a tractor system, or are they just converging on? How are those angles done?
It actually has to do with turbulent shear layer growth at the edge. You know, if you have, for example, a hose, right? Water hose, fluid density of 1,000, into air, fluid density of 1.8, depending on the 1.3, 1.8, depending on temperature and gas. The density difference is so small that you get this nice steady stream, right? You know, if you design it correctly, you can actually get a laminar stream. It'll stay coherent and go from one place to another. But try to do the same thing, water into water, right? So now you've got this shear being built up at these differential velocities, generates little tiny vortices that break up into turbulence, and they mix. And so what you get is two angles, a shear layer mixing here, and then the shear layer mixing on the inside. So you actually get these two cones that are at the same angles, and that's the classical turbulent jet. Very simplified model, very easy to analyze in closed form, and you'll get 90% of the way there, 80% of the time with that simplified equation. In this case, I can tell everyone, just based on the release conditions, what the maximum force is going to be, because momentum is conserved. Momentum is basically the mass momentum flux leaving an area times the area. That is force. That is conserved. It will never get higher than that. So I can tell someone if they can successfully lower a piece of hardware over a flow on my iPhone. I don't tell them that. I make them write a contract, but yeah. But first order boundaries, back of the envelope, scoping, bounding, huge, huge tool, and that is what a lot of engineers, even engineers, can't do. And that's what makes old dinosaurs like me useful. I include him, but he looks tougher than me. Any other questions? Yep. wish you all greatest of luck in getting through in your studies. I hope you find the work that you're passionate about and enthusiastic about for the rest of your life. So thank you guys for being a great audience.
Okay, I want us to talk to the grad students afterwards. And also, I did want to tell you guys, since this is relevant to the talk, one thing that we have been working on is a sub-plan under the physics bachelor's degree in computational physics. So, you know, maybe you guys will take advantage of it, but at least it'll be something up there running so that other students in the future can learn how to do some of this stuff. Good.
Good.
Thank you.
Yep. I'm going to turn off my microphone now.